All right, we're back. Um, Fancy new splash screen. Thanks, Pete, for that. Gives me time to get this thing actually going before I start rambling. Um, Gonna double check that it works. Um, and while I wait for that to maybe work, uh, I don't know that it's actually working. Um, yeah, probably not. Oh, there we go. Cool. Okay. All right. So back to the part tumbler. We made good progress earlier. So what we're going to do is focus on getting the parts made really. We have some last minute things to do. Um, Small things like getting some hardware fixed here on the bumpers and then getting into changing this motor because the last motor we had exploded and wasn't particularly good. So um, that's on the to-do today after I share this. And there's like a million things you have to do to get a stream actually going. Um, yeah, across 3 platforms, sharing and everything. Okay, so yeah, let's just get back into it. So these flanges gave us some trouble. And last we left off, we decided that essentially we need radial gap, but we don't really have the ability to do radial gap. I'm sorry, not radial, circumferential gap, because as you lay this wrap around the barrel, you start to get the tolerance stack up built up over each screw that we install, and eventually you get to the last screw, and you've only got, I think the distance here is something like 0.25 millimeters, 0.1 millimeters. So that's not good. We should fix that. So I don't know that we can though, but we'll try to think through some ways to do that. We will get into the pre-mirror version of the assembly so we can work on it, and then that'll propagate out once we get it set. To fix the circumferential tolerance stack up, I think we could just accept that we can open up this slot a bit and use washers to increase the effective head of the screw. I think that would work. We should be using a screw. We should be using washers here anyways, to be honest. So is there a quick way to fix? I guess we can just use an offset. So if we want to increase the diameter here, we might be able to make it, yeah, it's that easy. So we'll do that all around, I think. Or actually, what I'll do is I'll just draw a boolean and then modify all of the parts with a pattern. It's probably the easiest way to do this. But first, why don't we do a tolerance analysis to understand how much actual room we're going to need. Yeah, let's do that. I haven't done a TA or a tolerance stack or tolerance analysis, whatever you want to call it, um, in Python before. So a tolerance analysis, in case you haven't done one, is essentially a way to ensure that your parts fit. And there's a way to do this statistically using something called a process capability analysis. And what this does is it helps you understand. So when you're making, for instance, 100 million of a thing, when you look at the normal distribution of how the parts are going to be manufactured, you're going to have defects on both ends. And what a TA does, if you do it alongside a process capability analysis, is it ensures that when you make 100 million of it, you only have to throw, say, 30 of them away. But we're not going to do that because we're not going to make hundreds of millions of these things. We're only going to make maybe 1 to 5 of these things per build or per, I don't know, person, right? So like even if you're running a machine shop, you're gonna make like 5 of these, not 500 million of them. So what you do in that case is instead of worrying about the process capability index, what you would instead care about is the worst case analysis. So you can develop essentially a TA that is focused purely on, in the worst case, will it be, can you put it together? And so we know what the worst case tolerances are for a CNC laser process. So we can actually figure out what that'll have to be. The problem though is that I think that that's going to be really sloppy. So we might end up doing an RSS version of this. RSS meaning root sum squared. Yeah. So we'll do that. And we'll try it in Python because I've never actually tried it in Python. We'll be able to do it in Python because this is going to be pretty simple. Yeah, I think this is going to be pretty simple. So let's actually get that drawn up. Circumferential, what do we want to call that? Make this readable. So essentially what that's saying is you've got a flange here and you've got your barrel and you're going to have 6 more flanges or 5 more to make 6. And when you go to install this, there's going to be some tolerance. And so I think the tolerance for a CNC laser is something like 100 micron. It's probably 130 or 5 thou in freedom units. So that's saying from here to here, you'll have a positional tolerance of roughly, it's actually a profile tolerance to be honest. So writing this in GD&T terms, it's going to be something like profile tolerance of 0.13 or 130 microns relative to A, which if this is your diameter A that we're going to build off of, that's going to be 4.1. And then that will have a profile tolerance as well. Actually, it's going to have something. And then that is going to be datum A. And so, and then finally actually that'll be datum B, I think. That makes more sense. And then the datum A would probably be the surface here. And that's going to be something like, it wouldn't be, it's not going to be that, I guess we could just make it that surface, but I think the right way to do that is something like a flatness tolerance, but I don't think you can tolerance a flatness. Not a tolerance, but I don't think you can, what's it called? I don't think you can datum a flatness tolerance. I have a cheat sheet somewhere. Yeah, you can actually, you can do it. So what is the one you can't do it for? There's flatness, there's actually, I think the AI might be wrong here. I don't know that you can do this. I don't think you can build a datum off it. You can't do it relative to a datum. That's right. You can build the datum off it. Sorry. I don't like GD&T for the record. I need to know it and I have to use it, but I'm not a huge fan. So anyways, you build a flatness tolerance here. And then you would use that surface essentially to, we said this would be A. And then you would use that to develop a profile tolerance for this one. This, whatever tolerance this is going to be. I think it would be positional. Yeah, I think it'd be positional. This one ends up being profile. Again, not because it's the right way to do it. We would actually want to do something like a positional tolerance on this. But what happens is actually this one is the one that gets the profile relative to A. This builds your datum B. And again, we're talking about this hole here. And then from there, you can start to break out, okay, well then from here to here, and then from here to here, and then from here to here. And so then you can build your TA off of that. I haven't done one in a while, so you're going to have to struggle along with me on this one, but I want to make this quick because I'd like to keep going. So that's roughly what we're going to do here for the TA. And what to make this simple, I'm going to unwrap this barrel and make it a flat sheet. And so this actually turns into a flat sheet that has holes in it. And it's symmetric, so we're going to have them on this side. And then you're going to develop this hole as 0.1, and then you're going to just continue to do that all the way to your final hole, and there's 6. So we will have 6 essentially holes in the stack up here. And it gets more complicated because you actually have 2 parts. You have the sheet, then you also have your barrel cap, and that has 6 holes. And so I'm going to do this really rough and ugly, really rough and ugly. And I might actually have to throw this away because I do actually think that we don't have enough information here. I'm going off of essentially plus or minus, essentially what the machine is capable of doing. And like I said earlier, it's roughly, I believe it's a profile tolerance of 0.13, like I said. And so that's not necessarily enough information. So the actual stack up is going to be easy. The question is, how do we implement this for 2 parts? I think we might actually have to do a spreadsheet for this, but I don't want to do that. I think we'll just do it mathematically. So in other words, let's actually get going on the calcs, and I'll sketch over here as required. So we'll set up this profile tolerance. As something. So what is it going to be? Worst case profile tolerance on machining process. So They say it's something like, they say it's something like 130 micron. I think they're being overly cautious. So let's find out what it actually is. We're going to use CNC laser. Nothing on accuracy or positional tolerance here, or profile tolerance. Here we go. So we'll just search for tolerance and see what they say. This is for a T-slot, but hopefully they tell us how the actual design, how the actual process is designed for the correct tolerance. Worst case scenario, for a majority of our materials, yep. So they're saying 130 micron or 5 thou. Yeah, 130 micron. Which is actually sloppier than that, right? Because it's twice that, because it's plus or minus. So in other words, they're saying your surface could be here, or it could be 130 micron. So actually, you have the center of the process. You could be on the plus side to 130 micron, and then you can be on the minus side to 130 micron, which means you have a quarter millimeter or 260 micron of total position where that hole can be. Yeah. Yeah. Well, that's bad. That's really sloppy. It would be fine if it were 2 holes, but it's 6 holes multiplied by 2 parts. So it's pretty bad. Oh, but you know what? I think we're actually saved here, and I'll explain why. Let me show you why I think we're saved here. So the reason is because the CNC laser process indexes once and then cuts, and then it's relative to the datum of the first cut. So in other words, if you have a sheet metal part like this, and you have holes all over the place, it isn't like they're stacked up over the distance of the part like I was drawing here. They're actually stacked up such that you have 0.00 here, and then anywhere I put the head of that cutter, it's going to be plus or minus 130 micron. And it only happens once. So actually, is that right? No, that's wrong. It is what I said earlier. Yeah, it is what I said earlier. Like, I'll draw it out. So exaggerated. I have a hole here, and it's 130 micron in this direction, the wrong way. And then this hole could be 130 this way. But they're not cumulative. That's what I'm getting at. So I was right about the sheet thing here. It isn't cumulative. So all I have to do is design for the worst case. Yeah. So we don't need, so we can do worst case. We don't need RSS or process capability or any of that. We'll design to essentially the part stack plus the worst case for this. Okay, this makes sense. So in other words, This is what we're going to do. Simplified, we have two holes. And in red is the part behind it. And so this is nominal, right? And so you can't see the red because it's under this part and it's nominal. So they're line to line. But what I could have happen is that this hole underneath could be over here. And that would be this way 130 micron. Now, this hole could actually be over here, 130 micron. Right? So that's part one of the TA, is this. Actually, that's going to confuse, so I'll make this rounded. Okay, so that's part one of the TA. Now, not only do we have it on the hole, what happens to another hole? So let's say this is 130 micron in the wrong direction here. What happens to this hole? This hole could also be off. Yeah, that's what happens. Okay, so this hole could also be off 130 micron in the wrong way. And we could once again have the hole underneath be in the wrong way. Actually, I'll make this dotted as well to show that these are worst cases. And so we actually get this error stacked twice, or 4 times, I think. Let's think through that. So 130 microns. So the worst case is the top plate hole is here. And that's 130 microns in the wrong way. So we'll sketch this out now. We'll write this out now. Okay. So we'll write this out because we've got fancy pint. Okay, so we could have it TA1 value. We're going to call this, I guess we'll work in X. So TA, XTA for part 1 is that 130. And then we have the same, really, XTA1, yeah. And then we have the same going on for TA2. By the way, normally I would do this in Excel, but this is quick enough and I don't have Excel in front of me, so we're going to do it in Python. So let's think through that. So what's the worst case TA? It's going to be TA1. And that is this hole being here. Plus TA1 again. We'll call it sub 1, or 1 sub 1 for the first one, and TA 1 sub 2 for for the second one because this hole could be off in the wrong direction the other way. So that's equal to the TA stack for 1. And then for part 2, we're going to have TA 2 sub 1 plus TA 2 sub 2 is equal to TA 2. And then for the worst case, it's really simple. We just calculate these. And we're not going to do RSS. We're just going to do worst case, like I said. So this actually turns out to be, these are XTA. These are actually going to be, yeah. And we do that again. Okay, so the worst case is going to be XTA worst case is equal to those values added together. And we're going to format that. And I think it's, we said XTA worst case, and then we're doing, I think that's right. Okay, well that's really confusing, so we'll just do a simple print. (520 micron). So we need 520 micron or half a millimeter essentially for the slot width here. And if this were a drawing, we would actually do the actual dimensioning and tolerancing for that. But we're not doing that because essentially we know that they're going to hit that 130 microns and we're going off the worst case. So we're good. All right. 1 second. All right. So we have to turn this into a slot essentially, or upsize it. And so we did the upsize just now. Let's get rid of that. And we will change this to, we're at 4.1. And this is saying we need 4, so actually this 0.52 millimeters is applied radially. So the overall dimension increases 2 times this. So this 0.52 is actually, let's actually find the diameter. Um, is it diametral or diametrical? I think it's diametral, yeah. Actually, we'll just call this 1 millimeter. Sorry, no. That's the tolerance. So it's actually 4 for the nominal size of the screw plus that. So we need 5-ish. Yeah, so 5.04 millimeter. And so that is 5.04 divided by 2. So it's not the end of the world. It does open up, but it's not insane. So 5.04, this should be 5.04. Well, it is whatever. 5.04. Okay. And that, ladies and gentlemen, is how you calculate your required slot width if you're rushing through it and you're not making 100 million of the thing. You just do a quick worst case analysis on it. We might go into what it is to do a process capability analysis at some point. Because essentially, I think it is really useful to understand that because it delves into the deeper fundamentals of manufacturing processes and how you ensure your parts actually come together correctly. It's outside of the scope of this project, but I do think it's worth investigating. And so we'll actually probably do that. Got this new fancy mic, by the way, and I'm worried that if I like pull on my shirt, it's gonna make a bunch of noise. Sounds like it does, so I'll be careful. Anyways, yeah, it is valuable to understand the deeper manufacturing process impacts for this sort of thing. So whenever you look around, if you look around your room and find things that are complex and manufactured, for instance, my laptop or the IM parts for this fan, they're using something like that. They're using a process capability analysis to figure that out. And so they're looking at something called CPK. And what it does is it it informs you for a given, so when you run your TA for a given set of tolerances, over the course of your tolerance stack, what's the likelihood that the parts are going to fit? And so they chase numbers, and it makes it really easy to understand. So higher is better. Your sigma is the statistical significance, or what's it actually called? Sigma, I think it's standard deviation, right? I think it's standard deviation. But in probability, they have a specific name. I think it's standard deviation. Standard deviation, yeah. So for 3 standards of deviation, you'll want, well, actually 1.0. And that's saying 0.07% of your parts are going to fail. And so this is why you can see why when you're making lots of things, you want this number to be as high as possible. And so the whole trope of Six Sigma made by, I forgot who it was, Motorola or Mitsubishi or something, was because they wanted essentially the trailing nines to be so high that the yield was essentially infinite. Or in other words, you were never going to have failed parts. But for most folks, 93% is pretty good. So to put it in perspective, Comma AI, who makes that self-driving car device, their process capability index was actually less than, what were we just looking at? Their process capability index was actually less than 1. So in other words, they actually only had 2 sigma, I think. And so in other words, when they sold 100 comma 3s or comma whatever it was, they were essentially on a 1-year adjusted index, seeing I think something like 70% or 25% returns. And this is not insider info. I think George Hotz actually talked about this at a Comma AI conference a couple years ago, and they managed to get the number way up, and it was through things like what we're talking about here. By the way, that is not that number 2 sigma, that was actually kind of accepted in mass production, depending on which company you're talking to and the quality of the products. So it was, 30 years ago, not out of the realm of likelihood that there was a 30% chance you were going to have to return a product because something went wrong. Now we're talking about just parts fitting, but for developing a complex product, it's way more complex than do the parts fit. It's something like, do the parts fit, and is this antenna in exactly the right place so that it doesn't interfere with this one weird metal component that changes some RF behavior, right? So there's like a million things literally that can go wrong in a product. And this process that we're talking about in the context of designing for our little sheet metal barrel here, the context for that is pretty simple because it's just do these parts fit. But when you start to get to consumer electronics, you start to get into the realm of, well, you're not just looking at do parts fit, you're looking at what is the radiative emissivity of the anodization process, or anodizing process. Anodization is not a word, of the anodizing process. And that might sound too far into the weeds, but if that process is off by 20%, you just lost potentially, if you're working on space rated hardware, 20% of your thermal emissivity, which is essentially 30 or 20% of your total heat dissipation. So all of that stuff can add up. And so when you consider, well, I just lost 20% of my ability to get rid of heat, and it turned out that the processor or the controller was on the high end of the spectrum for producing heat, and that's 20% plus 20%, and now all of a sudden you've got 40% more thermal load in your components, and you can see where this is going. And if you do that 10 times, you're guaranteed to have failure. So that's why process capability index is so critical. But outside of the realm of our little part tumbler, so we're going to stop talking about that now, because I'm sure it's getting boring for everyone. But if you want to make a lot of a thing, you ought to learn what that is. So we have to upsize this slot. We found out how much it is. We are going to now copy this over. And I think the fastest way to do this will be to actually just generate that geometry and pattern that. So we'll actually create a Boolean for this. We're going to pattern that. Okay, and now we boolean. And so now all of our slots have that new fancy tolerance. 5.04 should be that distance, which it is. Great. All right. So now this should propagate over to the mirrored portion of the assembly. Yep. Okay. Real quick, because I did this the quick and dirty way, and it's simple because it's a two-part stack, I want to show you what it looks like when you actually go do this in the real world. That's not it. We don't use Reddit because Reddit is a slop pile now. Sorry, it's not a slop pile. It's a bot haven that contains AI slop. So it's going to look like this actually, but I don't like this. I think it's going to be, it really is an Excel spreadsheet with a diagram like this to show you what exactly is going on. I know I'm getting off track here, but I just want to show you what this looks like. When you see one in the wild, I want you to be able to identify what it is. Yeah, here you go. That's what it's going to look like. So you'll even include nominal in that. We didn't do that because we don't really care, but nominal will matter. Sometimes, I should say. It's also just nice to know what the nominal was, so it helps you set the context for what your plus and minus tolerance is. Because plus or minus 100 micron on a 4-meter part is a tiny little bit, but plus or minus 100 micron on the thickness of a part of 200 micron is a football field. So the context is useful. All right, done with tolerances. I don't like GD&T and I don't like tolerance analyses. I do them because I have to. Despite the fact I just spent 30 minutes ranting about them. They're necessary evil. Okay, let's get some washers in here because I do think we need washers. Okay, and then we'll pattern that 6 times. We'll need that washer because I think it's going to be getting a little tight here. Not tight, but the opposite of tight actually, technically speaking, for these slots. So I'm going to buy a little bit more surface area to engage that flange with. A cool car. Okay, so okay, so we want to do we want to wrap up the screw clearance on this. No, we don't need to do the slot detail because we just did the TA to prove that we don't need to. Detailing error, forgot slot bend. Yeah, we'll leave that here just as a reminder for later. We want washers on bumpers. Yes, we do have to do that. Yeah, let's just do that real quick. Actually, first, let's make sure that that hardware gets propagated correctly. then we'll move on. So we want to pick up those washers too, I think, in this mirror. I don't know the fastest way to pick up these washers, but let's see if this does it. I believe that's the fastest way. So now, if we roll forward, we should see washers, and we do. Great. So, washers on bumpers, let's get those in. So, let's see. Oh, I already added them. Yeah, I already added them. So that's done. Let's make sure they propagate it all around. Not that it matters, but yep, did. Change the motor. Okay, so this looks like a short list item, but it's actually going to be a bit of work. So here's the cross section that we're working with. So this is the new motor, which doesn't work. We want to bring back the old motor. And so the RPM of this was 20, and I do think 20 was about the right speed, but we could go a little bit lower. So I actually have the motors. I bought them ahead of time. But we'll want to pull in this geometry real quick. We're looking for this. Yes. So let's do that. Let's uprev that. Actually, no, we're not going to uprev this. This is a COTS part, so we don't need to uprev. So I will import this. So let's get this hardware fixed too. Now we'll import. So this is the new motor. Man, this is going to be a ton of work. Yeah, this is going to be a ton of work. Just now realizing. First, let me pull out the motors that I bought. Double check the dimensions. So, what if they have the actual specs written on these? So this one is, yeah, 30 RPM, and I think that was a little too fast. 50. That's even faster. All right. I think we're going for much faster. So that's good. But that's at no load speed. That's at nominal no load. What happens is when you apply torque to a DC motor for a fixed voltage, it actually reduces in speed, so this will lower when you actually load it. Remember, we did the calculations to show that for a gravity-limited tumbler, the maximum speed was something like 100 RPM, and we're at 30 RPM, which is a third of the maximum speed. The problem is it's going to be cooking. I'm actually a little bit worried about this, but we'll build and test. I mean, we did the analysis to show that it could be 100, so we'll trust the math. We'll trust the math. Anyways, so let's validate the dimensions. So we don't care about the motor versus reducer. We'll just get the overall length. So I think it's 60-ish millimeters. So let's verify that. Yep, 60-ish. It's a little bit bigger, but that's fine. We probably want to leave that. And that includes terminals on the back. Yeah, so that actually includes the terminals. And then let's double check the motor shaft dimensions, because it would be very disappointing if we found out that the motor shaft was not the same size as the CAD model. So yep, that is 6, and the rest will be the same there. And then overall length of the shaft, that also matters. It's 15.5, and we are at 15, so that's fine. And then that looks about right on the stub for the motor. Great. All right, so that's roughly correct. I'm happy with that. So this goes back into our inventory system. Our handy dandy trusty inventory system, which is my table. That is my inventory system. If it's on the table, it's in the inventory. If it's not on the table, I don't have it in inventory. I have to buy it again. It is a financial burden, but it works. Okay, so we have this new motor. Let's actually get cooking on this. So we will save our work here. Which version are we at? So this is B03. B03 is at C, D, 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 so we need E. Okay. So we'll wipe history here, keep things quick, get rid of these redundant planes. I'm going to be so happy if this barrel works. Really, I hope that the increase in diameter gets this fixed. This is so much cheaper. Can you hear me drinking? I'm sorry if you can. New mic. So fastest way is, I think we're going to move the control box out of the way. So we'll just move that. We've got our motor here, and we're going to get rid of this. Before we do, I want to know what this motor shaft was for, because that's going to help us maybe quickly size the rest of the coupling design. And I think these were the same. I think these were M3s. Yeah, and I think these were M3s as well. We'll check that. Just turn everything else off. Actually, maybe we want the frame. Nope. We want hardware. This was 3. Yep, so these are M3s. Knew that was right. And so we're going to have to carry this whole pattern over to start. First, let's get the motor in the right place. So we're going to mount the motor face to the bearing assembly here. And then we're going to find these screws. We don't need these washers anymore. And these, do they end up being in the right position? No, they do not. Decidedly do not. So let's isolate this stuff. Actually, just delete this. Get this out of the way. And delete these holes. And we will redraw with better holes. First, we'll make room for the motor stub, or the shaft stub. So it was a 12, so we'll make that 15. It doesn't need to be super... actually, we might want to use this to locate the motor. So on a traditional servo motor or something like that, you actually want to use that. There's going to be some central, literally central feature on the motor they use to concentrically align the entire well, the motor shaft essentially, because that's critical. And so it doesn't matter what kind of motor you select. So actually, this is great. There's like 4 types of motors here. And I'll show you. So so right here, actually, let me draw. So this motor right here, this feature right here is actually machined into the motor so that you can locate it accurately to the assembly that you are mounting the motor with. And every one of these motors has this. You can see this is all painted, but it's machined here, and it's specifically so that you can not axially, radially, aka concentrically align the motor shaft relative to this feature. And it's true here, and it's true here. Doesn't matter how you mount a motor, they're going to have some feature that allows you to develop accuracy, because you need that. Because imagine if this motor shaft was off by a millimeter in the wrong direction, right? It's not going to mate up with your motor coupler or your reducer or whatever you end up mating this thing to. So that's why that's so critical, and why every motor you buy will have that. Sorry, asterisk, every real motor you buy. Hobbyist motors do not have that. So we'll want to use that to locate. And as we said earlier, plus or minus 130 microns. So this is going to be 12 plus 2 times the 130. Takes us to 12.26. Yep. Okay. We can now look at this. This is going to be fantastic if this works as easily as I think it might. I think I might have spoken too soon, realizing that it's not. So let's get that hardware and we'll see why it's not going to be as easy as I would like. So I'm going to just copy essentially the screw hole, then take that through the part. Just taking that to the mating plate. And I'm going to pattern that. We have 6 screw holes, so we're going to pattern it 6 times. And that should line up, and it does. And then we'll put this screw in. And then we will pattern this 6 times as well. Okay. So that motor is now mounted and working. Now the trick comes when we look at the packaging, the existing assembly. And we have an issue. So this bearing cup right here actually interferes with these screws. So close. We almost were able to just swap this in with a minor change to the motor flexures here, but it's probably not going to work. So what are the solutions here? One is to move this entire bearing assembly off to create a gap. The second one is to just control to reduce the thickness of this part, but we're already getting pretty close on edge distance here, so I don't know if that's a good idea. Oh, we can actually leave the bearing assembly alone and eat into this gap here by just shifting all of this over. All of this being, we shift the geometry of the bearing the outer bearing cup and the inner bearing cup. I think that would work. So what's an acceptable gap? So right now we have a gap of 4.6 millimeters. It's kind of close. And actually we have less because we're using it to close. We're using this gap here to apply preload to the bearings. And that's a 1 millimeter gap. So that 4.6 millimeters is actually 3.6. And we know that this gapping works, so I'm reluctant to change this gap unless I have a very good reason, because that would introduce some uncertainty in our next prototype. I think we're going to just have to move everything. Yeah. All right. So what gap do we want? We'll call this 0. It actually looks exactly like 0, which is very rare. I'm surprised that it's actually 0. It's almost like I knew something when I designed it. So we'll call it, we had a 3 millimeter gap here. Let's just go for a 3 millimeter gap here. So we're just going to move everything 3 millimeters. We'll have to do that part by part now, but it should be fine. So we'll start with the right side and move left until we get to this gap here, to this part. Coincidentally, that's also a great way to think about TAs, if you're ever trying to generate the documentation requisite for that. Okay, so what does that mean? We're going to move everything 3 millimeters to get that gap. So how do we do that? So we're going to move all of these parts 3 millimeters. So I'm selecting all bodies and moving it 3. So that's all the bodies. Now, these parts are going to change. And I'm just moving faces now. 3 millimeters. So let's just draw a quick cross section to sanity check that. And it looks like that's right. We'll pull it back just a hair. Yeah. Actually, let's pull a new cross section. I don't think that was a good one. It looks right. So let me actually hide the control box for a moment. So, okay, we have this part extended. We moved the assembly here. Now, this barrel becomes a problem. So we need to extend the barrel 3 millimeters. So we move the hardware. We just need to move the geometry 3 millimeters. But we want it to be symmetric. So how do we do that? You know, honestly, I'm going to cheat it. I'm going to leave the barrel alone. And we'll just make up the distance here. This does mean my construction plane goes away. Regenerate that later, but we're just going to make up the distance with the gap here and here. So we'll extend this. No, this stays the same. So actually, we're just going to extend this inner motor coupler face 3 millimeters. And that does mean that I think the rest of the barrel actually changes. So let's isolate that. And so now I think all of this moves over 3 millimeters to made up with what we did earlier. Okay, so let's just do a quick double check. That gap looks right. That gap looks right. Hardware looks good. Let's pull a cross section through the barrel just to double check. All that looks good. Yeah, I think we're good there. And so this gap is going to increase. Let's see what's happening to that hardware first. So this hardware needs to move 3 millimeters, which I think we have enough room on the screws for. Yep. So now this face needs to move 3. Actually, wait, before we get there, let's look at this cross section and see what we're going to move. I think everything here moves. Yeah, everything here moves. This part changes slightly, but the rest of the parts just move. Doesn't mean we lose 3 millimeters on the engagement here, which I don't like. But we can make up for that. And actually, we should make up for that. So this part's going to change as well. So let's actually do that now. So this part extends 3. And it looks about right. This is goofy, but we can address that. Hell, we might even just leave that. How do we fix that? I think we extrude this 3. Then we move this face 3. I think that works. Maybe we can rotate this face. It's a bit of a pickle. Let's look at the cross section. We'll address that in a little bit. Just get the stack working, and then we'll get back to that. And this moves 3, but we want this flexure to live there still. So I think we move this face 3. Okay. I think that's working. We have to decrapify this little thing here, but we can get to that in a second. First, let's fix this motor. Fix this motor coupler geometry because the diameter increased. So we have to change these. And these are, what are the thickness? 762. So what we'll do is delete the redundant ones, isolate the motor, and then Boolean that to make this fast. Actually, can we just offset this? We might be able to just offset this. That might be faster. Let's try that. We are definitely going to break some DFM rules there. We'll get to that in a second. So yeah, the offset seems to work, which is good. Now, we do have to offset these, though. I don't know how to do that, though, without making a mess of this. We ran FEA on this, so we have to be careful. Huh. So let's find a circle that was conservatively intersecting everything we cared about, which would be this. Then we offset this circle 1 millimeter for that growth. We get this. So now we just fill this in, I believe. Okay, that should work. And then we'll clean this up. So we'll add our radii for that. Looks like 1 millimeter, and we're good. And as we said, we had 3 of these, so we're going to pull out the copy of the 3. Okay. I think that works. Okay. Yeah, that's I think that works. So let's move this hardware back into the right place. This part number is wrong, I think. Actually, that part number might be the same. So we had this at 30 RPM. So the part number stays the same. You just have to call out the RPMs. So we're going to rename this to GA37RG30. And I do kind of want to pick up this 24 volt version, but we'll get to that later. Okay. Pull that in the motor assembly. What are these? These are the flexures that have changed. So we'll pull those into the correct part number. And actually, we get to upred these, as we should. Pinion spacer plate. No, 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 no. We got rid of this. Where was this flexure living? step back in time and find that. It's in the bearing assembly motor flexure. Okay. Here it is. So we'll up rev this since we actually are increasing the revision. Actually, that's my versioning. I want revision. I mean, we want version. We want revision, not version. There's a difference. So we'll pull these in now. Right, so our flexures are fixed. That mates with the motor. Our gapping looks right. We have a clearance here to these new screws. Control box needs a little love, but first let's make sure this all looks right. I think it does. So now we look at the control box and make sure that that new motor fits. And it doesn't. That's going to be a pain to model. It looks like we do have room for it, as long as we don't interfere with these screws. Make sure I don't forget that. So maybe it's worth just growing whatever this was 36.2. The original was, where'd it go? The original was 24.8. So it was a diametral growth of 11.4, which is 11.4. So we grew by 6 in on each side. So that should simplify this redesign. If we just grow this 6 millimeters all around, should be, I think that's feasible. And I think this is symmetric, so I can actually just slice these. I think this changes too, so. Just quickly delete these so we can work on this. Actually, let's just do a sanity check. Does 6 millimeters interfere with this screw? If it does, then we have to think deeper about this, and it does. We're gonna have to change the bearing cup anyways. So these screws are gonna have to increase radially in distance by 6 millimeters. This plate is gonna have to increase radially by 6 millimeters. Because I think we break edge distance here if we go up 6. Yeah, we do. And it's actually not 6, it's more than 6. Because it's at an angle here. We have to fix this anyway, so might as well just do that now. So let's find radial. How do we quickly model this? Let's move this where we're gonna have to move it. and isolate this and think about how we're going to model this. I'll just quickly delete these. Yeah. And then I'll pattern the geometry. I'll leave the core geometry here, but then pattern the rest of it later. And this is not playing nice. Why? Why are you not playing nice? What's going on? Okay. Is that why? Nope. Direct modeling does have its downsides. For instance, when it doesn't want to play nice. I think it has something to do with, yeah, there we go. All right, so now we will move this 6. Let's pick some random number to now to start. Actually, that's not going to be enough. So this is a move laterally 6. I'll delete these. And actually, what's the fastest way to model this? I'm just going to make a copy and measure the distance. No, that's not going to work either. Crap. What's the fastest way to do this? So I need this hole to be over here. And it needs to be 6 away. All right. This is breaking my brain. The geometry of this is breaking my brain. Okay, I see it now. I see now. So we want this. We want this to be 6 millimeters away from its current position. And then this can be, no, this needs to be a horizontal constraint. Yep. And so now, no, that's still not working. I guess we have to draw it out. So this is 6. Because we want this away from that existing base over here. This is maintaining the 6 millimeters, and now we can extend this and make it coincident here. And now we're radially where we're supposed to be aligned to maintain this pattern. And we're still 6 millimeters away. Okay. And then the original, well, we should develop the new minimum thickness here, but this will be edge distance is going to be 2 times the diameter, and this is a 4.1, so this will be 8.2. There we go. make this stuff. Actually, I don't need this anymore. This is all construction except for that. This gets trimmed. These holes go away. And then we pull this hole through. And then we pattern the hole. Great. Now we can carry that through to the other parts and the screws. Curious, what was that change in distance? About 7. Patterning again. And then we want to fix this plate too. Fortunately, I think the fastest way to do this is going to be a sketch. So just leave this geometry. How are we going to do this? It's going to be easier if we get rid of these radii. Yeah. So now we pick up that edge and we bring it over here. What happened? There we go. Why are you not constrained? That's why. I feel like what just happened? Okay, there we go. We mirror that. Now we can adjust this. Picked the wrong face there. 2 objects. This is the object. That broke. The ability to extrude 2 objects was one of the first things that made me fall in love with NX. There are very few applications like Shaper3D and NX that let you do this. Fantastic. And we want to fix these holes. We're going to just delete them. And repattern this one. Here's the little trick. I love doing this. If you're working in plane on something like this hole, I want to be aligned with this hole. Because it's in its own plane here, you can actually just move point to point out of plane, and it's only going to resolve within plane. So that hole behind that you can barely see and this hole are going to snap together because it's ignoring the Z. It's very easy to do that. Highly recommend taking advantage of that workflow. Okay. And we are realigned. So we should be able to grow this out now by 6, and we should be fine. And we are. Great. We are getting close here, though. Glad we checked that. We're actually interfering with that pen nut now. So we actually have a reason to get rid of the fully circular sort of design on this bearing plate. So we get to do some weight optimization. Isn't that fun? So here's our symmetry. It's 120 degrees. And we want to maintain the edge distance here. And we want to bring this into some minimum diameter. Maybe we'll just start with the diameter that fits the center point. And we are going to subtract that. We'll make that into a boolean and then pattern that. We'll make it into a body to boolean. I keep saying that. And actually, we can cheat this by adding our fillets ahead of time. That should work. I think we can reduce this diameter. Looks about right. I do want to change that fillet though. Doesn't look skookum enough. That does. Great. All right, so we're still symmetric and we avoid the interference now with that hem nut over here. Perfect. Great. Okay. Get in there. So now we have to get that 6mm increase on the control box. And we might be able to just brute force this by doing a global offset of 6. It's going to break these, but we might be able to just move these. See if this works. I think it will. No. So 28.5 maybe? No. So we'll offset these faces. Maybe we have to do this one. Nope. Let's try these. Nope. And let's finally try this. There we go. Just right. And we'll change this to whatever the initial fillet size was, radius size was, which was 5.5. Why are you not playing nice? What's going on? Blend can't be processed. All right, we'll brute force that. Okay, and then these screws also move. And then this geometry does too. We'll get this on the back end. Make it easier to look at. Ooh, that's going to be tough. We have to increase this as well. And I think that's going to be nastier to deal with. Let's see what this does. Yeah, it's going to be nasty to deal with. So maybe we can do... Honestly, we're just going to brute force these and bring the holes back later. And now we boolean after we fix the screw placement. Right, almost there. So this cap is now fixed, I think. And we want to now do this one. Move that screw back. And then we will, this one will be easier, I think. We actually don't need this. And we can just move this to 6. Hopefully we can just move all of this stuff. We can. Great. Did this move? Yes, it did. Great. These are going to move as well, so we'll do that now. And I think that's it. Yeah, I think that's it. So now we can mirror this over, I believe. And Boolean, and we're done with the control box. So now that should fit the new motor. Ah, that's missing the cutout for this. So we should fix that. All right, and I think we're done. Fix the bearing cup. These need a move. These washers are in the wrong place. All right. Okay. I think we are done. Let's just snap some cross sections to double check our work. And we will get to cooking the parts. Oh, that doesn't look right. Looks like the holes didn't come through on this. Glad we checked. So yeah, the holes didn't come through on the control box. So let's isolate that stuff and fix that. See, we can probably get away with it by just increasing the diameter. Yeah, we don't actually want. Yeah, we don't actually want. Through holes on that, so this is actually interfering with the motor right now. So I'll show you. Yeah, you can see it's interfering there. So let's select that face. We said it was 36 to 38 would work, but why don't we give ourselves a little leeway because we don't really care about the positional placement of the motor relative to the housing. So that can be a little sloppy, but let's make sure there's nothing we're missing. Looks fine. Let's get that section back. So what else are we missing here? Bearing looks good. Look at the other side. This all looks good. Yeah. Does this interfere now? Just double check. No, but it gets awfully close. Gets awfully close. It's a little bit more gap. Looks good. Okay, back to sectioning. Double check our work. Yeah, let's just pull this through and look. It's looking good so far. Let's do the same for this side. Yeah. Just to double check, let's pull another section orthogonal to that and take a look at this. That looks tight, but that's okay. Yeah, that's clearance, all right. The bearing here. Flexures. Yeah. Is that? We need a clearance on these screws. Yeah, I forgot to add them. So we have one here for these screws, but not for the M3s. So let's do that. These are going to come up, yeah, 3 nominal. That's not good. So select all these holes and offset them. Give ourselves 100 micron. It's plenty. Okay. Yeah, still looks good. Yeah, that's fine. Okay, this all looks good. What is this? Did we mess something up? Those slots look wrong. How do these slots move? This moved. Oh, for that interference check. I forgot to reverse this back. Let's find that. There we go. And then let's double check the barrel, and then I think we'll be done. This is awfully close. We might have an issue there. That's awfully close. Doesn't matter. Yes. Yeah. No, I mean, as long as we have a millimeter, we have half a millimeter. That's a little too tight. We're gonna have to move that. So how are we gonna move that? So this part is going to, so we're gonna make a midplane again, so we can work around it. Delete these. Okay, so we're gonna give it a millimeter of clearance. And that's gonna increase the size of the size of the flexure as well. But actually, I guess it doesn't really matter, so we'll leave this alone, but we're still gonna wanna move these slots. So we'll give it, actually we'll make it 2 millimeters. And it doesn't change the geometry of these parts, it just moves them. So I'll just move them. I think set 2. So that looks aligned now, and then we will mirror this stuff over. Okay, and I think we're good now. Healthy clearance there. That looks good. I'm really worried about this not working. There's no reason it has to extend past. So maybe we get rid of some of that leeway. So we'll give it 5, -5. Looks better. Okay. Let's finish our section check and we'll wrap it up. Do we need prelit on this? No, we do generate prelit on the inner ring, and that's fine. I think we're fine on this. We actually want this to be a little released axially, so we're fine. Okay, I think we're good. Oh, we need to add the ribs back to this outer bearing cup, and then we're done. So half of 120 is, actually it's not 120. What is this? I thought it's 120. It is 120. So why is 60 wrong? Oh, it needs to be 30. That's right. Okay. And then we are going to intersect this here. So at its widest, we want it to be the distance between these two, and so we'll call that 3 millimeters. Have that. All right. Then we extrude that through. We inverted that. We don't want. Huh. This is annoying. Here, we'll do it this way. I'm essentially adding a draft angle here. So we actually want this to go away. We want it 3 at the base. And then our draft angle will make, we want that angle. So we can do it this way. 180 minus, we'll just give it a 3-degree angle. And actually we'll mirror that to make this simple. Okay. So now, extrude that. Okay. So now we boolean this, but is there a way to, if I mirror this, if I pattern this, I don't think this is going to work. No, it's not. Brute force this. Just trying to add a stress relief detail here. That's what you're seeing. So now we can fill out this. Do this to both sides. And now we can get rid of some area that's not going to do much. Get rid of some volume that's not going to do much for us in terms of strength. And we will then pull this back. And then brute force that boolean. Non-mod. Hate when it does this. Almost there. Just have to pattern this 3 times and we're done. If I stop breaking the instructions. Okay, now we're done. Join all this. Delete that. And we're good. This might actually, we should just add some fillets here. Continuity's sake. Okay. Those stiffener ribs I do think are necessary to keep the bearing cup stiff. Okay, now we're done. We're done now. And we will save our version and we will timestamp or rev stamp this and we will go get this made. I think we're at E before or D before. I think we're at E. No, we're at F now. All right, clean this up. This goes to bearing 2, bearing block 2. And this was bearing plate. Yeah. Okay. Okay. All right. So tomorrow we will get this manufactured and we will move on to another project. I have an idea. So, all right. Thanks for joining, and I'll see you next time.